Awesome. So let's get started. As you all probably already know, so today I'm going to talk about some Rust in the Kubernetes space, right? I do want to give out a disclaimer. I'm not a Rust expert because I see Nick, coming up after me, who is probably a Rust expert. I'm more of an intermediate Rust person, so keep that in mind. Cool. Mhm. So, small introduction. Of course, Stephen gave me a good introduction, but just so that I go through my regular script. So, my name is Deepu Sasidharan. I'm the co-lead of JHipster. It's a nifty code generation platform or rapid application development platform, the Java world. I'm also a Java champion, quite recent. So it's it's also a bit weird that I'm here talking about Rust, but that's all fine. I also created a nifty dashboard called KDash for Kubernetes, among many other open source stuff. I'm an open source aficionado. I have been doing open source for, I think, 7, 8 years now. I'm also a polyglot developer. I work on Java, JavaScript, TypeScript, Go, Rust, among others. So I don't discriminate between languages, not much. So I work at Okta as a developer advocate with a focus on DevOps. I also frequently write on my personal blog about tech topics, so you can find it on deepu.tech if you're interested in my content. You can also follow me on Twitter if you want to get updates on content I publish. I have also written some books, mostly around JHipster. So yeah, and you can find most of my social handles on the screen. So let's get started. So before we go into the topics of how Rust fits into DevOps world and how it is better than Go and all those things, I want you to introduce you to something I built. So it's called KDash. So it's a simple terminal dashboard for Kubernetes. It provides common resource views, node metrics, logs, and so on. I can give you a quick demo. So this is I'm gonna. It's a CLI dashboard. Basically, reads out from your Kubernetes configuration, and it shows you a kubectl kind of view, but more interactive. So there is full keyboard navigation. Where you can go through stuff. You can switch between contexts. You have a really nice utilization view that shows utilization for your entire cluster, which is quite handy in my opinion. You can also do basic stuff like switch between your namespaces. See basic memory CPU usage on the screen. There are more stuff like log streaming, for example. If I go to Mhm. Yeah, if I go to pods, I can go into the pod. I can stream the logs from there, for example. Of course, you can get your describe or describe as YAML and all those things. So yeah, that's about it. So that's the tool. So let's get back to the yeah. So the utilization metrics is something that you probably won't find in many other tools. So that's like a highlight feature that is built into KDash. I wanted to show you that so that I can ask this question and I can set some context, right? So I built KDash, the CLI tool KDash, and was my first serious Rust project. So I have been, going through Rust stuff, learning here and there a bit of Rust, trying, small things. I never had an opportunity to build something holistic. So I was pondering over what to build, and I finalized on building a KDash, and I built it in Rust, and I learned a lot of Rust while building KDash. I have to say it was a really fun experience. I never had so much fun in the recent few years working on anything as much as I did on KDash, and I think most of the credit goes to Rust being an awesome language and the developer experience of working with Rust being so awesome that I was like addicted to working on that. I would wake up early mornings sometimes with some idea on my head, and I'll start coding. So that is how interested I was in building that using Rust. And I have, in my career of like 12 years or something now, I had never been that excited except from the earlier years of my career in coding and building something. So that was a really fun experience, and all credit goes to Rust, as I mentioned, right? So the question would be, so why did I build another Kubernetes dashboard, right? Because there are so many solutions already out there. I mean, kubectl itself is already quite good, though it is not interactive. It's already quite good enough. And there is also the K9s project, which is built in Go, but it's very similar to KDash. And of course, it offers way more than KDash. Like, it offers CRUD actions on your K8s resources, whereas KDash is mostly view only, right? And I don't think it's quite obvious, right, that KDash is inspired by K9s, because a lot of features are very similar. The UI is slightly similarish, though I try to make it a bit more user friendly and a bit more easy to navigate and everything. But it's heavily inspired by K9s. So when I started learning Rust, I wanted build something which is more than hello worlds and to-do apps. And I wanted something serious, something that has a good architecture, something which will have a lot of challenges. So I decided to also build something that could be useful, right? So and since I'm on the Kubernetes space a lot, I thought it would be nice to build something in the Kubernetes space, so that I can also kind of POC the idea about using Rust for Kubernetes tools. So I was also using KNS, and there were some things that was some things I preferred to be better, and in terms of user experience, in terms of speed and stuff. So I thought it could be a nice idea to build something similar, since there weren't many other projects similar. Especially, there was nothing in the Rust space. So I decided to go ahead with that. The focus when I was building KDash was definitely UX and navigation. That was the primary goal. Of course, the speed and everything just was add-on provided by Rust, right? So that was not the focus. So simpler user experience and navigation was the focus. But of course, in the end, when I finished, without doing anything or without spending any effort, I did also get way better efficiency. Like, KDash uses much less resources than kubectl. Of course, then much less resources than K9s, but also then kubectl. Even if you're running kubectl commands on watch, it will still use way more resources than KDash. Of course, it's not like too meaningful when we talk about in megabytes, but still it uses way more resources than KDash. So that's all from Rust, for free. And the obvious question I get after when I talk about this, the obvious question I always get is, why Rust and why not Golang? Because most of the stuff in the Kubernetes world is built using Go, right? And even Kubernetes itself is built on Go. And most of the tooling, the infrastructure around Kubernetes is all built in Go. So, and it has, Go has a lot of libraries to help build Kubernetes ecosystem tools and stuff. So why not Go? Why Rust? What advantages do you get, right? That's a valid question. And since most of the Kubernetes space is built with Go, honestly, Go is an excellent language for these purposes, right? And there is not a lot of solid reasons to choose Rust over Go for a user space project like KDash. That's a different thing. But there are Kubernetes use cases where Rust is a way better choice than Go. Some ideal examples would be sidecar applications, like a proxy, similar to Linkerd or Envoy. Linkerd proxy is already written in Rust. So proxies, sidecars are like applications that would live alongside your pod, in your cluster, and they have to be lightweight, they have to be fast, they cannot have a lot of overhead, so that they don't slow down your actual applications. So sidecars are ideal use cases where Rust would make a lot more sense than building in Go, for example. These days, sidecar applications mostly are either built in Rust or in C++, because efficiency and speed is the huge importance. So Rust would be ideal for these kind of projects. In-cluster tools like log aggregation, monitoring, eBPF, building Kubernetes operators, WebAssembly workloads. These are also use cases where Rust would be a much better choice than Go when it comes to building the Kubernetes ecosystem. right? But for user space projects like KDash, for example, it doesn't make that much of a difference. You can build it in Go or Rust. In the end, more or less, there won't be a huge difference. Of course, the Rust version might be more efficient in terms of resource usage. It might be a bit more faster, but for user space projects like a CLI, I don't think it matters that much. And the real reason I chose Rust for KDash was, of course, to evaluate Rust as a evaluate Rust in these kind of use cases. And also, I wanted to build something a bit more complex in Rust to see how it works, to get the ins and outs and stuff like that. So overall, I do believe that Rust is an ideal candidate to build out the Kubernetes ecosystem, along with Go, of course, because Go still has value, and adding Rust into the mix would only make the ecosystem better. We would have a lot more much more safer applications, faster applications, and so on. There is already a lot of things coming up in that space. We'll talk about that in a while. In my opinion, when we talked about the ideal use cases, right, and even for user space, if we have to nitpick, then definitely there are a lot of advantages that Rust offers, right? Again, I'm not going to go into details because I believe most of the people tuning in are familiar with Rust and they know what Rust is and everything. So I'm just going to go to a few things that I consider quite important. Of course, safety would be the number one benefit, right, of using Rust over Go. So memory safety is currently like one of the biggest issues that we have, right? Memory safety related issues are like cause of majority of security CVEs we encounter. Undefined behavior can be abused by a hacker to take control of a program or to leak privileged information, right? In memory safe languages, if you try to access an array element out of its bound, you'll just crash the program with a panic or error, which is predictable behavior. Whereas in memory unsafe languages like C, C++, which we are still using to build, like sidecars and proxies, like Envoy proxy, for example, right, still being used. So there is a lot of chances of introducing security vulnerabilities, right? And these stats kind of, if you put this together, it's like memory safety issues are causing like more than 70% of CVs we encounter across platforms, across products. So why do we still fall for that, and why do we still use memory unsafe languages to build tools like proxies and stuff like that? So in my opinion, Rust can be a boon in that area, especially to build out such what do you call, like sensitive applications, or like such integral applications like proxies, especially for service meshes and so on. So for me, safety is like the number one advantage of Rust over Go. So memory safety, of course, thread safety also causes issues. And I think recently there was, thread safety and also type safety. So I think I put this in the wrong slide. This should have been in the thread safety slides. Yeah, so recently the Microsoft team found some issues with Helm, which is written in Go, race condition issues, which would never happen in Rust, right? So these are the safety guarantees that Rust gives us, which would be very helpful for us. So Helm is a user space project. So even for that, Rust still would make it better. Though ideally it may not make it way better, like in terms of proxy or something, but it still would make it better. So the safety thing, and my most favorite thing about Rust, hands down, is like the zero cost abstraction features, right? So I assume most of you already know about this, but just to summarize, so in Rust, one thing I loved when I was working on Rust and when I was writing the project KDash in Rust was I didn't have to constantly worry about picking the right approach. For example, I didn't have to worry about, hey, should I do this as in function? Should I follow functional programming approach, or should I do imperative programming? Should I do object oriented? I didn't have to worry about any of this because it didn't matter. In the end, the style of my the style in which I programmed didn't matter, because the zero cost abstractions ensured that regardless of how I wrote my program, the end result was always as performant as it could be, right? Which is not the case in many other languages. Like most other languages, I think except for C++, I think no other language offers zero cost abstractions like this in this way. So I think that was quite freeing in my experience. It took away a lot of the thinking process that you would normally have to do. So I didn't have to worry about that. I could just have fun in coding. Like I could go like ahead and like do whatever I want. Of course, like not talking about doing bad programming practices, but at least I could go, like go ahead and do full-fledged functional programming without having to worry about any performance impact. Or I could create layers and layers of abstractions, and I didn't have to worry about these creating performance impact. So that was like one of the greatest thing that I experienced and I liked about Rust, which I think is way undervalued feature, I would say. For example, right? Like, so I'm a long-term Java programmer as well. So you can see on the left is a Java program, on the right is a Rust program. Both are doing quite similar stuff, right? So it's doing factorial using three approaches. So there's a factorial using traditional for loops, like the imperative way. There is a recursive way, and there is factorial using the inbuilt functional APIs. So in case of Java, it's the stream API, and for Rust, it's the inbuilt functional APIs like fold in this particular case. And if you look at the benchmarks, so I ran benchmarks for both. For the Java benchmark, you can see the factorial with loops performs the best. It's obvious, very obvious, right? Because imperative code, in most of the cases, imperative code will have better performance because there are less indirections and there are less abstractions, right? And then the recursive one was twice, like twice as worst, if that's the right way to put it. And then finally, the inbuilt functional approach was like a slightly bit more slower. So of course, that's expected. This is expected in language like Java or language like Go. Most languages, especially high level languages, which does its own memory management and whatever. So this is to be expected. Whereas in the Rust version, the performance for the loop and recursive versions were almost identical, and the performance for the inbuilt performance using the inbuilt functional abstractions was even higher. And I looked into, I was surprised at first. Then I did some digging around, and I found that okay, the inbuilt a lot of the inbuilt abstractions also have additional bound checks and these things that improves performance. Of course, in my naive sample implementations, I didn't do any of those. That's why there is additional performance. But the takeaway is that because of zero cost abstraction, the style is not going to matter. So you can go full functional, you can write imperative, object oriented, whatever. It doesn't matter. It's going to give you the same performance once it's compiled, and you don't have to worry about it. So that's like the one of the best features of Rust in my opinion. So of course, there are a lot more other things that I like about Rust. For example, the tooling and community is one of the best that I have encountered. Like, I have worked with many languages, and so far, I don't think I have come across any other language which has such nice compiler, such user-friendly tooling like Cargo and the entire ecosystem, and also the community, such helpful and vibrant community. So that's definitely another plus point for us. The tooling is way better than Go in my experience. I have done some serious development using Go back in the days, and huge projects with like a medium-sized team, and the developer experience of using Go doesn't even come close to the developer experience of using Rust. So that's also another plus. I don't want to turn this into a Go versus Rust thingy, so let's move on. So of course, high level languages versus lower level languages. I think you all know the difference. So Rust kind of sits in the middle, right? Because most high-level languages will give you a choice between safety, speed, and abstractions. You can only choose two. So if you take C++, you can get speed and abstractions, but not safety. If you take Java, you can take safety and maybe maybe speed, a little bit of speed, but no abstractions probably. And if you take Go, then it's the same, right? So that trade-off is not present with Rust, because you get safety, speed, and abstractions. You get all three, and you don't have to choose. So that's where I think Rust stands out among other languages. So also, again, this research has some controversies around it, but a 2017 research which compared speed, memory efficiency, and energy efficiency of programming languages put Rust in the top five. So in terms of course, speed and time, Rust was like a second, right behind C, which makes sense. Because the speed would directly correlate to energy. Of course, it didn't fare that well in the memory usage, which was contested, because in real world experiences, even in my personal experience, the memory usage of Rust was anecdotal evidence, of course, but I didn't have a case where Rust was using more memory than Go, for example, right? So this could be based on the implementations they chose, and of course there was I think there was some difference of opinion in the community about how the implementations were done, but it's still good to know that Rust is quite energy efficient, which makes sense because it's quite fast. So in my opinion, people won't appreciate Rust unless they spend few weeks building something in it. So the initial steep learning curve is there. It's a thing. So it could be frustrating or challenging depending on how you see it. For me, it was challenging, but I can also see that it could be frustrating for someone if they are just trying to get something done, right? But once past that point, maybe a few weeks in, I think it's hard not to love Rust, right? It's like a toddler with superpower, right? And honestly, writing Rust code is much more pleasant experience overall, like compared to many other languages. So I really like this quote from Tech Republic, which I think is really is quite true, I would say. So let's get into some use cases and the ecosystem that we have in terms of using Rust with Kubernetes, right? So we spoke about WebAssembly. I didn't want to go into too much details of WebAssembly because I believe there was some talks around WebAssembly and Rust in the past in the meetup, so I don't want to go too deep. But the WebAssembly system interface, or WASI, makes it possible to run WASM workloads in Kubernetes. And it's still quite new and has a lot of rough edges. I wrote a blog post about it. You can find the link on the bottom of the slide. It's quite rough. It's not definitely not production ready, but it could be the future of a containerless Kubernetes, because WebAssembly would make Docker containers obsolete, because they both do the same thing, but WebAssembly containers or WebAssembly OCI images, you cannot call them containers. So like WebAssembly, right? It's its own format. So WebAssembly gives the same advantages as containers, but gives more sandboxing, more security, and stuff like that. So it's like a better alternative to containers. So if this technology gets adopted, gets a good ecosystem around, there are still some issues like networking is a mess currently, so those needs to be taken care of. So once all that happens, I think WebAssembly on Kubernetes has a bright future and can make containers obsolete. Of course, not talking about like in the short term, but in the long term, because migrating from the current world of Docker is not going to happen overnight, right? So that's going to take some time. But when we talk about WebAssembly and WASM workloads on Kubernetes, of course, you can build WebAssembly WASM binaries using any supported language. You don't have to do it in Rust. But Rust has one of the best tooling and ecosystem for WASM. So and that makes it an ideal language to build WASI workloads for Kubernetes as well. So by that argument, because it has one of the best developer experience for doing WebAssembly, and has like a lot of libraries, tools, and stuff. And another reason is a lot of the current infrastructure around WASI or WebAssembly on Kubernetes, especially, is built using Rust as well. So that is going to spill over in terms of tools, libraries, and stuff like that. So that's going to also make it a nicer experience to work with Rust, in my opinion. So, for example, Wasm time is a JIT style standalone runtime. This is what makes it possible to run WebAssembly on Kubernetes, for example, because WebAssembly was originally meant for the web. It was a web. It was meant for web, and it was meant to run in browsers. So, in order to run it outside of a browser, you need a runtime, and Wasm time is one of that runtime, which is open source. It is written in Rust. It's still kind of not production ready, I would say, but it's a runtime that is being used by many other projects at this moment. There is also a few other runtimes. There is Wasm Edge, which is a runtime focused on microservices. It's more commercial oriented. It's focused on microservices. It is built using C++, but also offers Rust binding so that you can directly build against that, like applications against that in Rust. So and there is Wasm Cloud, which is focused on distributed actors rather than workloads. It is also written in Rust. So all these three runtimes will let you work with Rust, and it makes they all provide Rust bindings. I mean, two of them are written in Rust. That means you can directly use them in your Rust project. Wasm Edge provides Rust bindings, so you can also use that in your Rust project. So it makes it easy to build stuff for these runtimes. And finally, there is also Crustlet, which is based on Wasm time. It's a kubelet written in Rust and can run OCI, so Wasm binaries in the OCI format. So Wasm binaries can be built as OCI images, open container images, though they are not containers, but you can still build them as OCI images, and you can run them using Crustlet. And the blog that I have linked down here, it explores that particular use case using Crustlet to run Rust WASI binaries, right? So WebAssembly is one area that I'm looking forward to, especially in terms of seeing more of Rust here. And that's one area that I'm keeping my eye out from a Kubernetes plus Rust enthusiast point of view. So the next use case would be in cluster tools, right? Proxy, sidecars, service mesh. We briefly spoke about this. Of course, Rust is going to make it much nicer in terms of course, it's going to be fast. There's going to be better safety than using C++, and it's going to be efficient, right? And so it makes it ideal for building sidecars, proxies, service mesh infrastructure, stuff like that. So Linkerd is already a very popular proxy. So I think Linkerd and Envoy are the two most popular proxies in the Kubernetes world. And Envoy is written in C++ and Linkerd is written in Rust. So Linkerd was originally written in Go, which was later migrated to Rust, which makes sense. Then another use case would be K8s operators, right? So Rust asynchronous programming model is a perfect match for building high performance or high throughput or highly parallel operators. So you can have operators which are doing parallel processing without having to worry about race conditions and stuff. You can build high performance operators. So this is another use case area where Rust would shine better than Go in terms of performance and in terms of ease of use. It's going to be light on resource usage and footprint, and also it's going to be way less code to write. Writing an operator in Rust and Go is going to be different experience, because with Rust you can, once you have some basic so macros or something, then building out new operators would be like quite straightforward and very little code compared to how you do it in Go, for example. Another use case would be log aggregation, monitoring, eBPF, and these kind of things. So especially in a Kubernetes container where you want your resource usages to be kept minimum so that your applications can have more resources, it makes sense to build crawlers or log aggregation agents and these kind of things in Rust, so that they take very little footprint They don't impact too much in terms of performance, and they're quite fast as well, right? Another area would be eBPF, which is the current kind of the ideal way to collect logs, or for observability, right, in the Linux kernels. So there is already a solution called RedBPF, which is a tool chain to work with eBPF, which could mean that in your Kubernetes setup, you could use this to build, I don't know, log observability solutions, monitoring solutions, logging solutions, security solutions, and so on. So these are all the use case that I'm kind of envisioning for Rust in the Kubernetes space. And of course, there is finally user space tools. I won't say this is the most important aspect, because in cluster tools and WebAssembly would be the most important, and is use cases where Rust can actually add a lot more value than the current solutions out there. In the user space tools, of course, you can build stuff using Rust. It's not going to have too much of an impact compared to building in Go or something, but it's still possible. I mean, I built KDash using it. There are a few others which are quite nice. Like there is QB, which is a Kubernetes context switching and prom modification utility for your shell. There is kubectl view allocations, which is a library that I have used in KDash as well to see your Kubernetes usage metrics and stuff like that. And then finally, there is Click, which is a command line interactive controller for Kubernetes, more like a REPL for Kubernetes. So these are, and there are a lot of other smaller user space tools, and of course, anything that you can build in Go, you can also technically build in Rust. So for a Rust programmer, it shouldn't stop you from building Kubernetes tools. Just because you don't want to write it in Go doesn't mean that you don't have other options. You can still write it in Rust. And of course, for this we would need a library ecosystem. There are quite some. I won't say it is as good as Go in terms of the diversity of libraries, but most of the important ones are already there. For example, KubeRS, which is the Kubernetes client for Rust. So I use that in KDash. KDash. So this is equivalent to the Go Kubernetes Go client in terms of features and everything. It doesn't have some bells and whistles, but since it is written in Rust, we have really nice generics and macros and stuff like that. So the library also provides some generic traits and stuff, which you can easily extend to bridge whatever gap you will find. For example, when I used the KubeRS library, the metrics API didn't have any implementation in this, whereas the Go version has a metric API implementation. And so I was like thinking, I don't have this, or should I use another library? Should I use my own? Should I just build my own bridge between that? But then I went to the KubeRS issue list and opened an issue, and yeah, then there was a really nice suggestion. Hey, we have this generic trait, just implement this and you're done. And that's it, like 5 lines of code, and I was done. So even to implement a feature that was not there, it only took like 5 lines of code, like using that generic and providing some configuration, and that was done. So it's as easy as that. Of course, KubeRS uses K8s Open API underneath, which is the Rust bindings for Kubernetes. Then there is KubeRT, which is runtime helpers based on KubeRS. There is the R operator, which makes writing Kubernetes operators in Rust very easy, because it provides macros and stuff for that, which you don't have to like it provides most of the boilerplate. Then you have Risotto, which is a Rust SDK for AWS, and of course there is also the official AWS SDK for Rust. And there is a Prometheus parser to parse and validate Prometheus query expressions. Of course, there are a lot more smaller libraries you would find. Of course, you'll find a lot more libraries. I just listed the ones with a lot of users, or like a lot of downloads and stuff like that. A lot of smaller ones. But the ecosystem around Kubernetes for Rust is still evolving. I won't say it is unusable at this moment. It is still. I have seen a lot of production examples of these libraries being used. So it is as good as I won't say it is as good as the Go ecosystem, but it is getting there. I think in few more years, I think this would be as good as the Go ecosystem. So this would be ideal time to actually start considering Rust for Kubernetes-based use case. How much more time do we have? I
Deepu, don't worry about the time. We are perfectly fine. It's
Okay.
6:15, so we are listening carefully to what you tell us.
Okay. No, this was like I had some optional slides. I wanted to make sure if I have time to go through them. So I think I have a few more minutes to go through. So that's fine. So yeah, I did want to touch up a little bit on the KDash architecture just to show it wasn't all hunky dory. So I just wanted to go through few things I learned on the way. Um, so K dash, yeah. So of course I used a bunch of libraries. So I did want to mention them. So TUIRS was like one of the best UI libraries that I have worked with. It's so nice. So it helped me build a rich UI on the terminal. So that was really good. So it's like what are those the old I forgot the name for it. What are they? Okay, never mind. Then there is Crossterm, which is a terminal manipulation library, which is used by TURS. TURS supports few other terminal manipulation libraries as well. I went with Crossterm so that I can add support for both Windows, Linux, and Mac. Of course, Tokyo is unavoidable in any Rust project these days because KDash is fully event-driven and non-blocking asynchronous stuff. So, like, yeah, Tokyo was like a obvious choice for that. And of course, kubers with K8s, OpenAPI, OpenSSL, and all those stuff. kubectl view allocations for some metric stuff. Clap for command line argument parser. Used a few other smaller libraries like Rust clipboard, Serde for serialization and stuff, and Ductor. So these are the libraries I used. And data architecture wise, I started out with something simple like any other person trying to learn Rust. And soon I started getting roadblocks and started learning more and more about asynchronous Rust and stuff like that. And in the end, decided for something like KDash, it made sense to make it completely event driven so that there was nothing blocking and since I was using Tokyo, it was quite easy to split everything into multiple threads. So there was like one thread which was just taking care of rendering the UI. There was another thread that was taking care of network requests, and there was another thread that was taking care of parsing commands and like running commands and stuff like that. So I think there are 3 or 4 threads, and there is one data store, and I used Arc plus Mutex for a shared state data store. So that I mean, of course, in Rust, it was so easy to do this because didn't have to worry about data races and stuff like that. And having Arc Mutex as a single data store with multi threads and event-driven architecture made it simpler to show the data and like to update the data and stuff like that. I didn't want to go into much more complex data structure for that. The threading is a bit more complex than it is, but again, Rust plus Tokyo made threading so easy that after a while I even forgot that I was working in a multi-threaded application where I had normally, like for example, if I was doing the same in Java, JavaScript, or something, or even Go, I would have to be so much. I would have to pay so much more attention into data races and not corrupting data from multiple threads and stuff like that. Here, didn't after a while didn't even have to worry about it. And honestly, I forgot that I was working in a multi-threaded asynchronous application. And of course, non-blocking UI and stuff like that, thanks to multiple threads and event-driven I/O. So the only bottleneck I faced was the network I/O with the Cube API server, which is because the API server itself is not working in a non-blocking asynchronous way, right? That is the only bottleneck I still have. So I'm hoping that will improve on the library side, and this part will be better. It's not noticeable, but if you do too many network requests, you can sometimes see the bottleneck. Of course, there were challenges like log streaming was like the most challenging part for me. It was because the way log streaming was provided by the underlying kubers library didn't work with the architecture that I was trying to implement. So because it was blocking, and I had to do a lot of work around. I had to switch around a few Tokyo plugin libraries, so that I can add polling, retries, and these kind of things. But yeah, in the end, a separate thread for streaming and switching to Tokyo streams helped with some of the issues that I was facing. There are still some quirks which I haven't ironed out yet. I'm assuming that as I learn more and as I become better in overall Rust async world, I can fix some of those. The UI was initially blocking before I split it into multiple threads. I had one thread for everything, and the UI was you could notice bottlenecks on the UI because the UI will become unresponsive whenever there is a network call being done and stuff like that. So splitting into multiple threads helped with that. And another issue is that the version update of Kubernetes, because Kubernetes, K8s Open API, and anything that uses these, like any other library that uses these, has to be carefully updated. You cannot have multiple versions of K8s Open API in the same project because of how that library is published. It can only support one Kubernetes version at a time. So if there are multiple libraries in your project using the same libraries, then you will have issues whenever you compile. You'd have to play around. You'd have to play around and make sure that it works. And even if you do that, again, when some library updates a version, it could break again. So that part is still a bit of a what do you call, like a challenge. I haven't found a proper solution yet. For one of the library that I was using, I worked with the author of the library to to find a solution. We have some sort of workaround solution which works for now, but this could happen for anyone, I would assume. So I think that's it from me. Thank you so much for letting me share my experience and to share my love for Rust. If there are any questions, I'll be happy to answer.